9.4 Significance tests for a proportion. There's a four-step process for significance tests. We want to state the hypotheses, parameters, significance level, and evidence, which is our sample statistic. We want to plan by identifying which inference method that we're going to use and checking conditions. Now, the inference methods that we learned in the last chapter were one proportion z intervals and one sample t intervals. Now we'll have one proportion z tests and one sample t tests. So really the only wording that's changing is interval becomes test. When these conditions are met, we're going to perform the calculations. We're going to find that sample statistic, find the test statistic. Our sample statistic is the p-hat, and our test statistic is the z-score or t-score. All right, for these problems, the proportion ones, they're z-scores. And then we'll use that test statistic to find the p-value. Lastly, we're going to write our two-sentence conclusion where we either reject or fail to reject the null hypothesis, and then write our second sentence about having sufficient or insufficient evidence in support of the alternative. As I just noted, a significance test for a population proportion is often referred to as a one-sample z-test for p being a proportion, or a one-proportion z-test. So this section is really an extension of the last, where we're completing start to finish hypothesis tests for proportions. So in this problem, we want to see what proportion of people watch the TV show Survivor. Your textbook author, Mr. Starnes, states that 35% of all US adults have watched Survivor. A skeptical editor believes this figure is too high. So if it's too high, it's actually going to be less than 35%. That will be our alternative hypothesis. He collects a sample, random sample of 200 adults. 60 say, yes, I watched Survivor. Does this provide convincing evidence at the alpha equals 5% significance level to reject that null hypothesis and confirm the skeptical editor's beliefs? So the first step in our four-step process are to state the hypotheses, parameter, significance level, and alternative hypothesis. So our null hypothesis is p equals 0.35. Our alternative is that it's less than 0.35. P in this problem is representing the true proportion of all US adults who have watched Survivor. It told us the alpha level was 5%. If it didn't give us an alpha level, this is always the value that we're going to default to. And then the evidence in support of this alternative hypothesis is that the p-hat from a random sample is 30%. That's smaller than 35%. So we want to plan everything out. So the method that we'll be using is a one proportion z-test. We have a random sample of 200 US adults. 200 is less than 10% of all US adults. And when we check our large counts, remember that we're using the null hypothesis value of p equals 0.35, not the p-hat value of p equals 0.30. Okay, so these are always done with the null hypothesis value for hypothesis tests. So that's our p. We have 1 minus p, and we get 70 and 130. Those are both greater than 10. We're going to move on to our calculations. So we'll identify our sample statistic. This is our p-hat, and it comes from the 60 out of 200 people in our sample who said, yes, I watched Survivor. Next, we find our test statistic. This is our z-score. We're going to take our p-hat, and we subtract that null hypothesis value. So this is our p-hat. This is our p from the null hypothesis. Our standard deviation on the bottom here is from that sigma p-hat equation, radical PQ over N. Okay, so we have P and Q in there, not P hat Q hat. All right, so we're not using that P hat in those actual calculations. Now, just as a refresher as to what we're actually doing here, we're creating a normal curve around our null hypothesis value. So that 0.35 from the null hypothesis goes right in the middle. We also use that 0.35 to calculate our standard deviation, which we see down here. And then we find how likely is it for us to end up with our sample result. Is that unlikely? So we find a z-score for that. We would get negative 1.48. We look that up in our table, and we get a p-value of 0.0694. And as a last step, we're going to state our conclusions. It's always a two-sentence conclusion. The first is about the null hypothesis. Our p-value, 0.0694, is larger than the alpha level of 5%. And because of that, we're going to fail to reject the null hypothesis. When the p-value is smaller than alpha, that's when we reject it. Make sure you're using this wording along with the justification. Our second sentence is always about the alternative hypothesis. So when we fail to reject, that means we have insufficient evidence, or we do not have convincing evidence that the alternative is true. And our alternative was that p equals 0.35 is actually too high, and it's smaller than that. So there is not convincing evidence that the proportion of all US adults who have watched Survivor is less than 35%. As stated in the last video, even though we fail to reject the null hypothesis, we're not allowed to state that it is true. It's not leading us to believe that it's true. So in our sample, we had 30% that said that they watched Survivor. That's less than the 35%. So it is giving us some evidence that the alternative is true. However, it's not convincing. This result of 0.3 wouldn't be unlikely to occur just by chance alone. We would expect that to happen just by chance, and the fact that sometimes we're going to get a little more than 35% and sometimes we'll get a little less than 35%. This is something that's not surprising based on this distribution. In other words, this result can be explained simply by natural sampling variability. The other explanation is that we've made a type 2 error, where we're failing to reject a null hypothesis that's actually false. So in this situation, the alternative would be correct, it would be true, but we don't have enough evidence to convince us. There's nothing that we did along the way where it was a mistake. It's just that sometimes we end up with results where we make a type 1 or a type 2 error. Now, this has been talked about along the way. When we have a one-tailed test, we have a less than or a greater than alternative hypothesis. That's telling us the direction of the tail. So a less than means we're shading to the left. Greater than means we're shading to the right. If we have a not equal to, it means we're doing both of those things. So our test statistic would give us some value, negative 1.48. All right, we would find this one and we would just double it. All right, so we mirror it on the other side. Let's take this example here. We want to perform a test where the null hypothesis is p equals 0.3. The alternative is that it's not equal to 0.3. We have a sample of 50 that includes 19 successes. So that's giving us our p-hat, which is 19 out of 50. All right, it's telling us that the random and large counts conditions are met, which means we don't have to check them. And it's asking us to find the test statistic and the p-value. So our p-hat is 19 out of 50, or 38%. Our null hypothesis was that p equals 30%. So when we make our normal curve, we're going to put that p equals 30, or 0.30, I should say, right in the middle. And we're going to use that to find that standard deviation. Okay, the p-hat is where we start shading. So we want to find out, is that an unusual result? Now, with a not equal to test, it's not giving us a direction left or right. So we're always just shading this out to the end. And then we're going to mirror whatever we get on the other side. So we do 0.38, that's our p-hat, minus the null hypothesis of 0.3, divided by that standard deviation, which is based on that null hypothesis. And we get a z-score of 1.23. We're going to look that up in the table. And that's the right-tailed test portion of this. So we would have to do 1 minus when we look it up in the table. And we get a p-value from just that side of 0.1093. So that's just this right side. And whatever we get on this side, we put on the other side. So we just double whatever we get, and our p-value is 0.2186. And to round off the section, we'll do one more start to finish. So here we have some information from the CDC website saying that 27.5% of all high school students used e-cigarettes in 2019. Anton wonders if the national result holds true in his large urban high school. So he collects a random sample of 150 students, finding 29 of them who have smoked an e-cigarette. Is this convincing evidence at the 5% significance level that the proportion of all students at Anton School have smoked an e-cigarette that's different than the national result? So we'll start off by stating our hypotheses, parameters, significance level, and evidence for the alternative. Our null hypothesis is that the rate at his school is the same as the national level. The alternative is that it's different, maybe higher, maybe lower, we're not sure. P is going to represent the proportion of all students at Anton School who have smoked an e-cigarette. We're going to use an alpha level of 5% as stated in the problem. And we have our evidence for the alternative. 29 out of 50 is 0.193. That's not equal to 27.5%. We're going to complete a one proportion z-test or a one sample z-test for P. Those are the same thing. And we want to check our conditions. It was stated this is a random sample of 150 students. We'll assume that this is less than 10% of all students at a school. And when we check our large counts, we're going to use that P equals 0.275 and 1 minus 0.275. That's the P from the null hypothesis, not the P hat. We get values that are both greater than 10. So that condition is met. Our sample statistic is the P hat. It's calculated by doing 29 out of 150, 19.3%. When we make our normal curve, that 0.275 goes right in the middle, and we use that to calculate that sigma P hat PQ over N. Okay, so that's the standard deviation of our sampling distribution for a size of 150 students. As a reminder, we're always taking the P hat, and that P, that null hypothesis value, is always the thing that's coming after that minus sign. We get a z-score of negative 2.25. So when we look this up, now this was on the left side. All right, so we're right now shading in the left tail there. Okay, so we look this up in the table, and we get a p-value for that particular tail, 0.0122. Whatever we get on that left side, we're also going to put on the right side, meaning we're just going to double it to get a p-value of 0.0244. And lastly, we write out our conclusions. So we have a p-value that's smaller than the alpha level. Because the p-value of 0.0244 is less than alpha equals 0.05, we're going to reject the null hypothesis. So that result would be unlikely to occur if students at his school smoked e-cigarettes at the same rate as nationally. And because it's unlikely, we're going to reject that null hypothesis, stating that it's the same at this school as the national rate. When we reject the null hypothesis, we have sufficient evidence or convincing evidence for the alternative. So we have convincing evidence that the proportion of all students at Anton School who have smoked an e-cigarette is different from the national proportion of 0.275. Now let's tie this into what we did last chapter with confidence intervals. So with hypothesis tests, we're answering a yes or no question. Is the rate at Anton School different than the national rate? Based on our hypothesis test and a small p-value, we conclude that yes, it is different, but we're not given any information about what the proportion at his school actually is. And to do that, we would have to create a confidence interval. So this is what we did back in chapter 8. We have our p-hat, okay? We have our z-score for a 95% confidence interval. And then for a confidence interval, we're going to use that p-hat and the q-hat. In our standard deviation. So we're not using P and Q because we just concluded that P is incorrect. So we wouldn't want to use that when we're concluding that it's different at his school. So we go through our calculations and we would find, or we would conclude, we are 95% confident that the true proportion of students at Anton School who have smoked an e-cigarette is between 13% and 25.6%. As a reminder, this is giving us the plausible values for the proportion of students at his school that have smoked an e-cigarette. So somewhere in the range of 13% to 25.6%. And this confidence interval is just going to confirm what we found in our hypothesis test. Our hypothesis test was saying that proportion was equal to 0.275, and we see that 0.275 is not included in this interval. So based on this interval, we would reject this null hypothesis. So we can make these same conclusions, and we did back in chapter 8, right? When we're comparing what's inside this interval to something that's outside this interval. If it's outside the interval, we're going to reject it as an unreasonable estimate for that population parameter.